Hello. In today's lecture, we are going to understand a technique to solve the performance relationship that we had developed in last few classes for the IPR, WPR and CPR, how to club them to get the operating condition at a particular node. That will be done with the help of the nodal analysis. It is a Schlumberger patent, very simple technique, and you will see that when we are going through in today's class. But before going further, let us understand what we did so far, and even before understanding overall picture of the production system, I would like to solve a problem on CPR. So, the choke performance, its application we understand in the last class, the flow through the choke, we can estimate the unknown parameter, and that is where the concept of the critical pressure ratio was introduced that decides how to choose a particular flow regime that is happening in the choke and what type of the mathematical expressions should be used to estimate the unknown parameter. So, in this example, as it is mentioned here, we are having restrictions in the pipeline, and that restriction is actually, let us consider it is a choke with a lesser diameter. So, the diameter of the choke is very less than the diameter of the pipeline, and that is where the isentropic process is happening. So, let us say what is given to us to solve a particular problem. So, the gas information is given to us, that says the specific gravity of the gas is 0.6, that depends on the composition of the gases, and the specific heat ratio, that is K, in sometimes it is referred as a gamma, is given as 1.3. So, the information of the gaseous compositions are given to us. The diameter of the upstream choke are given to us, and it is specified what type of the choke device it is orifice type choke. Further, if we see what other information is required and given to us, it is upstream pressure, upstream temperature given to us. So, in this upstream is here, upstream, and this is downstream, flow is happening in this direction. So, upstream temperature, upstream pressure given to us, downstream pressure is given to us, and let us see what is asked to solve, what information we can get. So, we can calculate the gas passage rate, the production rate of the gas per unit time. That time could be the day, month or whatever, but standard condition is per unit day. So, we can say daily passage rate is asked to solve, and the downstream temperature, as we understand it, under the isentropic process condition, because of the Joule-Thomson effect, the pressure may go down and the temperature should be recorded, should be monitored, just to make sure do we need to employ the heating or not to prevent the ice plugging or the hydrate formation. So, let us, this is the way the problem is defined to us. Now, if we go further, what the first step we do, we calculate the critical pressure ratio, because the flow through the choke is determined by the critical pressure ratio or by the Mach number in other terms, but in terms of the pressure, it is a critical pressure ratio that depends on the specific heat ratio value of the gas that is being passed through this restrictions. So, as given to us the gas specific heat ratio as 1.3, we can calculate the pressure critical pressure ratio, and if we put the numerical value, we will get 0.5459. What is the pressure ratio given to us? In case of upstream downstream value given to us, we can calculate the actual pressure ratio or downstream to upstream pressure. It is 200 is the downstream pressure and 800 psi is upstream pressure. It comes out as 0.25. So, let us see what this ratio tells us when we compare it with the critical pressure ratio. The flow could be subsonic flow, we are having the mathematical equation for that, and the flow can be sonic flow, we are also having the mathematical equation for that. But which one should be used, determined when we compare the pressure ratio with the critical pressure ratio. So, let us see what we do. We say this is my pressure ratio upstream to downstream to upstream. So, this is 2, this is 1, or we can write it P down by P up, and pressure is in this direction. So, if we say this is Q versus either capital Q or a small q, Q versus pressure ratio, what type of the flow regime we can get. So, if I compare this, when I say my upstream pressure is much higher than downstream pressure, it means I am having almost the ratio close to or tends to 0, I am having the maximum production of the gas. That is happening here, and when the pressure ratio downstream to upstream are same, for example, the P2 by P1 is 1, we are having no flow from this, and everything is happening in between. There is a point that we call the critical pressure ratio, that is the value we got for this particular case is 0.5459. The value depends on the gas composition. At this particular point, what we understand from our understanding of the isentropic process, we say at this point, if we draw the relationship between the pressure ratio and Q, we see the curve is like this. It means when the pressure ratio is lesser than the critical pressure ratio, we are having a constant flow rate. That is a sonic condition or the critical condition we say. And on the other side, we are having this drawdown with respect to the pressure ratio, and we call it subsonic condition. So, in our case, in the numerical problem given to us, we see our 0.25, the pressure ratio is lesser than the critical pressure ratio. It means we are in the sonic region, our restriction is being operated in the sonic region. We should choose sonic flow equation to characterize or to represent the flow through the restrictions. So, this is the equation that is going to be used, and in this equation we can see what exactly we are having. We can calculate the flow rate Q at a standard condition. The numerical value again depends on the parameters are defined in a particular unit. So, let us take, we understand what is the numerical value going to be here. The important part is C and A is the area, C is the discharge coefficient, that should be known, and that needs to be calculated if it is not given to us. That depends on the type of the orifice, and then rest other things we understand, we know the gamma z is the specific gravity of the gas, K is specific heat ratio, T up is the upstream temperature. So, what we can do the next, we can calculate the value of C. The value of C, discharge coefficient, can be calculated with the help of the information given to us, and that simply says the discharge coefficient depends on the Reynolds number, and if Reynolds number is not known, we cannot calculate this C value. So, for that purpose we can assume the Reynolds number value. Why we need to assume it? Because Reynolds number depends on the flow rate, and we are supposed to calculate flow rate. So, what we are going to do? We will assume some Reynolds number. Let us say the Reynolds number very high, where the value of discharge coefficient almost become constant. So, if we take the Reynolds number value is greater than 10 to the power 6, or let us say we are assuming it is 10 to the power 6. So, what we will do? We can go to the chart or particular equation to calculate the discharge coefficient as discussed in the CPR class. We will get the value of discharge coefficient 0.62. After putting all this information given to us, we can get the value of Q, but that value of Q is correct or not? For that, what we need to do? We need to recalculate the Reynolds number using this flow rate, and if the Reynolds number is in the range or is in a tolerance range, we can say the assumption made was correct. Otherwise, we have to assume, we have to recalculate the Reynolds number, we have to calculate the discharge coefficient. Based on that, we have to calculate the Q again, and that is the way we can calculate the discharge rate. Next point is temperature, downstream temperature. So, we understand how to relate the upstream and downstream temperature for an isentropic process. It is a very simple case. When we are having the real gas, we have to calculate the compressibility factor on both condition, upstream condition and downstream condition. If we put all those non information in this, we will get the value of downstream temperature, and if the downstream temperature is very low, yes, we need to apply the heat. For this case, we are getting the value of downstream temperature is 5 degree Fahrenheit, that is lesser than 32 degree F. Yes, we need to apply the heat across the restriction. Similar here, the Q, what we are going to get is, as a numerical value I can provide you, 12,743 MSCF per day. So, I think that is clear the picture how to choose particular model equation to represent the flow through the restrictions. Now, if we move further, let us see what we understand so far about our production system. We see that production of the natural gas happens in this manner when we are having the radial flow under certain assumption what we discussed so far. Under the radial flow, we are having the fluid or the gas is being passed from this or being flowed from this porous media by the pressure gradient, and the pressure at the sand face is PWF. We also call it is a bottom hole pressure, and that is PWF. The flow is happening from PE to PWF. That is also depend on several factors we discuss in detail in the IPR relation. From here it is going to this part where we are having the WPR valve performance relationship. Again, because of the gravity will play a major role, it is a several thousand feet pipeline, and because of the mechanical energy balance equation we could set up the WPR relationship here. For this case WPR, this is we call this IPR, and this is top part where we just solved one example and we call it a CPR. So, the mathematically we can say how several parameters are going to affect the Q, similar for the WPR and chalk for performance. So, now we understand each segment or the three segments of our production system and how they are going to relate it, what the common factor they are having, and how to use one type of the relationship to assist the other relationship or find out the parameter those are not known will be discussed in today's lecture. So, in today's lecture if I go further, this is about gas well diluviality using nodal analysis. So, the well diluviality is, for example, the well diluviality means at what potential the gas well is having or the reservoir is having, what rate the gas can be produced from a gas well is estimated with the help of gas well diluviality analysis. But in this case, as if you see in this overall picture, our gas is being flowed from a several pressure zone, from a porous media very high reservoir pressure to wellbore pressure, from wellbore pressure to PHF wellhead pressure, and at the head we are having the choke device that is again reducing the pressure, means again pressure changes happening there. Throughout this temperature also changes, and because of that, as our gas is a compressible gas, its properties changes, and those properties are dependent like properties like compressibility factor Z and the gas viscosity mu depend on pressure and temperature, and they need to be calculated at a particular temperature pressure condition. That particular temperature pressure condition could be the average or could be other mean. To simulate the fluid flow in the system, so what we can do, we can divide this system as we did to understand the mathematically what is happening in a different nodes. We can break down the system and the fluid properties are calculated at that node by either taking the average of the pressure or temperature or just specifying that particular pressure and temperature known at that condition, we can calculate the fluid properties. The system analysis for determination of fluid production rate and pressure, because overall it is a pressure versus Q flow rate relationship. So, we can establish that relationship at a particular node with the help of the nodal analysis, and this is Schlumberger patent and widely used in petroleum engineering just to have the understanding of the reservoir or the well exactly, and at a particular operating condition, if the well is being produced, what will be the flow rate, or if we want to achieve that particular flow rate, what will be the pressure at that condition. This analysis can be used to forecast the production in terms of the pressure declination, what will be the rate the fluid can be produced or the gas can be produced, and the same time the what will be the cumulative production from the system. All this will be discussed later on, maybe in a separate lecture when we can discuss the system performance. In this lecture, we are going to understand the nodal analysis, and the nodal analysis works on the principle of pressure continuity. So, for example, if we choose any particular point and we come to this point from the right to left or left to right, if the information is continuous, in our case the information is pressure. So, at a particular point the information or the pressure will be the same, does not matter we come from this side or this side. This is the concept or the core concept of the nodal analysis, that is called the continuity of a pressure or pressure continuity. In this case what we say, if we are having like one way of the information is going like in this direction left to right, or in our system we are having the IPR to WPR to CPR. So, at a particular point when the information is coming we call it inflow relation, and when the information when it is moving out of that node we call the outflow information. In our case we will be using two location, that is the bottom point and the wellhead points, bottom hole point and wellhead point, where we will be establishing the nodal analysis. So, the nodal analysis can be done with the bottom hole or the wellhead point considering the nodal point. So, the prediction of achievable gas production rate from gas reservoir with specified string characteristic means other information, those may affect the flow regime production are considered like constant. For example, the string conditions or the production string condition, the diameter and other parameters were considered constant, and under a particular condition when the flow is happening, what will be the operating point at this bottom point or wellhead point will be estimated with the help of the nodal analysis. So, when I said the inflow curve, when the information is coming and when the information is going out, because of the continuity of the information, in our case pressure continuity, the intersection of these 2 points will give us the operating condition at that point. Our operating conditions are the pressure at that node as well as the flow rate. So, let us see if we are considering the bottom hole node, that is here where we are having PWF. At this node the inflow relation is the IPR, that IPR that is relate the reservoir conditions and the flow through this porous media to wellbore. So, here the inflow performance relation is IPR. We understand IPR could be in a different form. It could be in a quadratic form if we talk about the empirical expression, or could be in a back pressure form. Here what is written is in the form of back pressure. We also understand from our IPR correlation class the Q and pressure relationship can be expressed with a several approximation P, P score or MP. For a simplicity we are taken here as a P score approach, but the similar analysis can be implemented for the P approach and MP approach. And what is the outflow performance for this node? Our node is bottom hole, the outflow performance relationship is WPR. The information going out in the form of WPR, the information coming to this point in the form of IPR, and the intersection as per the nodal analysis, the intersection of these 2 points. So, tell us what are the operating conditions at this node, bottom node. So, let us see when we are having this IPR curve for inflow and when we are having this TPR or WPR relationship for outflow. What we see, the common point between this and this is PWF, and we can substitute PWF from one equation to other equation. Let us see what we can do. So, from the IPR equation what we can do, we can adjust this equation in the form of PWF score is equal to P bar score. This P bar is reservoir average pressure, sometimes it is written as a PR also or PE also. So, this PR bar a minus QSC by C to the power 1 by n. So, now from this expression we can substitute this PWF here. PWF can be replaced with the help of this expression, and what we will get is P bar score minus QSC to the power 1 by n on the left hand side, and the remaining we can also adjust this equation keeping 0 on the right hand side. So, now we got the mathematical equation that is relate IPR to PR, and we are not having PWF in this expression, means we could eliminate PWF. assuming that was not known to us, with the help of two equation we could eliminate the PWF. Now, if we can solve this equation, we can get the relationship between how my Q is going to be related with a different PWF conditions. This equation can be solved with a numerical technique such as Newton-Raphson iteration for gas flow rate QSC. So, now if I understand, if I know what is my reservoir pressure, I know what is my PHF at the wellhead conditions, other information given in this can be estimated with the help of some iteration procedure. Why the iteration procedure is required? You can see the QSC is here also, QSC is here also in both the terms, as well as some other properties like, for example, compressibility is calculated at average pressure, that should be known. Other than that, the S that represents some term in the WPR equation also account for flow rate as well as gamma g. This F, the friction factor that depends on the Reynolds number depends on the flow rate. So, it is a equation that needs some numerical iteration that can be done with the help of the Newton-Raphson method, but if we can do that thing, yes, we can calculate the flow rate. And once the flow rate is known, either the IPR or WPR can be used to calculate the what is the PWF at that particular node. Another way could be, we can plot this inflow equation on a curve and the outflow equation on a curve, and when these two curves are intersecting each other, we can get the operating condition at that point. So, let us see how it can be done with the help of an example. So, the example simply identified some of the information that is required to construct this IPR and WPR curve. So, for example, the gas compositions or the properties related to gas are given to us. The tubing through which the fluid is being flowed in the WBR are given to us. Wellhead conditions are given to us. Bottom hole temperature is also given to us. What is the reservoir pressure is specified, and C and N constant in back pressure equations, C and the exponent in back pressure equations are given to us. It means simply with this information what we can understand, the IPR relation used to characterize this flow is in the form of the back pressure, where C and N are given to us. We can choose either the P square or MP approach, but as we can see here, the reservoir pressure is 2000 psi, and we understand if the reservoir pressure is around 2000 or below 2000 psi, we should go with the P square approach. So, we can choose the IPR in the form of P square, and that is like here. So, the inflow curve is IPR, that is in the form of the pressure square approach in a back pressure form. The outflow equation is WPR for this case, because the information given to us, from with the help of that we can construct the WPR curve also. But in WPR curve you see the S is given, and that S is gamma z L cos theta z bar T bar, whichever the bar here is calculated at average conditions. We need to calculate the average temperature, average pressure. At that average pressure we can calculate the compressibility. Another important point is this F, and this F can be calculated with the help of either the chart or with knowing the Reynolds number. We can use some mathematical expression, those are given in the literature, to calculate the value of F. That F, remember this F can be either a fanning friction factor or Moody friction factor. In our case, it is a Moody friction factor. So, the Reynolds number that depends on several parameters. Here the simplified form of the Reynolds number from this equation, where we got 20.09 gamma g q by d mu. Viscosity is given to us, diameter is known, but we do not know QSC, that is we are trying to calculate. So, what we can do, we can assume some value of the QSC, calculate the Reynolds number, and Reynolds number can be put there to calculate this F value here, and every time we have to correct the value is correct or not. So, with this help, assuming we can calculate S, we can calculate F, we know everything. So, what we can do, we can construct the inflow curve here, and the outflow curve with the help of the second equation. And when we are going to do, what we are going to get, let us see. So, from this equation what we are having for the IPR, we can simply say the QSC is related to pressure in this form, and there will be a situation when my PWF is, so this is my PWF, this is my flow rate Q. So, when my PWF is 0, here what I am having the maximum flow rate. So, when my PWF is 0, I am having the maximum flow rate. So, let us say this is 0, this could be the maximum flow rate and we call this AOF. And when my PWF is reservoir pressure, that will be the situation, assume here PR bar, I said this is equivalent to P bar, or sometimes it is denoted as PE bar, we are having this point. And we can see here, depend on the value of the C and N, the curve can take a particular shape, and most of the cases this is like this. And similarly, we can construct the curve with the for the outflow also. When we know all these parameters, we can say how my PWF is related to Q. Yes, of course, the iteration may have to be done for that case also. And in that case, if we see, this is a reservoir pressure given to us 2000 psi, this is the maximum flow rate, that I can give you some quantitative value that will come out as 1912. 1912 unit is MSCF per day. So, we know when there is no flow is happening, when absolute open flow condition is there, and the PWF is represented by this. So, how to calculate this curve when we are having this relationship? So, what we can do in the IPR curve, we can either divide this flow rate from 0 to AOF in 10 equal parts and can calculate PWF with this from this equation and construct the curve. Or what we can do, we can calculate different, we can assume different value of PWF from reservoir pressure to 0, and accordingly we can calculate different value of Q. So, by either mean we can construct this curve. In the outflow curve, similar we can do when we are having different flow rate between 0 to EOF, we can put it here, do the iteration and can calculate. So, it comes out as when there is no flow is happening, your pressure is here is around somewhere here, and the value that is coming out at this condition is around 1050 or something. But as we are increasing this very slightly, the pressure PWF is increasing when we are having the different flow rate. So, this is our IPR or inflow curve at that particular node, and this is WPR or the outflow, we also call it outflow curve. And the point when these two are intersecting can be used to find out what is going to be PWF, the operating condition, and what is the flow rate at that condition. We can construct the curve to estimate the gas production rate. If we want to control the gas production rate, we can control with the help of PWF, or other way, if we want to control the PWF, we can control with the help of Q. But important point came out from 0 to AOF. This information gave us when there is no production is happening. If such situation is happening, we are having the P curve, we can get this, and when there is an absolute open flow condition, maximum production is happening, the curve nature is like this and other curve is like this. And as I said, how to draw this, I will just repeat it again. So, for example, Q, we can calculate the IPR parameter and WPR. The IPR parameter, both are pressure, we want to calculate PWF from both the equations. The Q, which we know will be 0 when there is no production is happening, and the maximum AOF situation. Between this, we can calculate different value, we can assume equally divided, and accordingly we can calculate the PWF by the IPR, PWF by the WPR, and the value those we are going to obtain here and here will be used to this to construct this thing. and with the help of this we can get the operating condition under that situation when we are having other parameter are constant in both the IPR and WPR equations. This is going to be the situation for PWF and Q. For the numerical case that we discussed, the Q is around 1478 or 1470, depend we are using the graphical procedure or we are using the mathematical. There is a slight difference depend on the how good optimization we could apply or iteration we could apply for this mathematical equation, and the pressure is around 1050 psi. So, I think with this I could explain how to use IPR and WPR to have the bottom hole operating conditions. The another is, as discussed, the node could be chosen as a wellhead, and what is the inflow relation for this wellhead? Whatever is coming from this side and what is coming from this side is WPR, and the WPR can be clubbed with the IPR to get the combined information that is coming to this node, and that wellhead node, the information in our case is pressure, that we are saying PHF, wellhead pressure, and the information going out of this is characterized by the CPR. So, now we understand the inflow relation is IPR plus WPR, and in the last problem, last example, we had understood if we club both the equation, we are going to get this kind of the relationship when our P reservoir pressure P bar is related to PHF. Similar, the outflow curve, that is here the outflow information is CPR, and we could have this expression where Q is related to PHF, the pressure at the wellhead. This expression depends again what type of the flow we are having in the choke device, that may be the sonic and subsonic. We are assuming this is a sonic flow. The equation can be replaced with the subsonic flow if subsonic flow is existing at this particular node. Important is, now we understand the inflow relation and outflow relation at this particular node, and using this, using these two equations, we can calculate the operating condition those are going to be at this particular node. We understand now we can do it either by the mathematical expression when we are clubbing both the equations, making one equation, doing certain iteration to calculate the flow rate, and then after knowing the flow rate we can put in either of the equation, inflow or outflow equation, to calculate the PHF, the wellhead or the pressure at that node. Or another way is again simply we can plot the inflow and outflow equations, and the intersection point will be the operating condition at that node. So, let us see, if we adjust this equation, outflow equation, take out the PHF, this can be arranged in this way. So, just PHF is kept back here, remaining has been transferred to the left hand side, we are going to get this expression PHF. Now, this PHF can be substituted from here to this equation, the inflow equations. What we are going to get? A very big expression, and this expression simply says, yes, I can be solved numerically. You just have to do the iteration, that can be done again with the help of Newton-Raphson method or some other way to get the QSC value. Okay? And you see here the QSC depends on several, this C, N, those are the IPR parameters, reservoir pressure, average temperature, average compressibility, whatever the parameter those characterize flow through reservoir to wellhead are included in these equations. So, we can solve it, but other procedure is again same, we can go with the help of the graphical procedure where the inflow and outflow are plotted. So, let us understand this again with the help of the example. So, the example simply says the gas specific gravity and other information related to the gas compositions are given to us, means what type of the gas is being produced, tubing diameter, means the valve conditions are given to us. The additional information that is given is choke device, diameter means size of the choke device and other information, that simply says we can use this information at the well head node to calculate the operating condition at that particular point. So, let us see what we can do. Similarly, we can do the inflow performance relationship. That inflow performance relationship is like this. We know now how to plot this, how to solve it. We know how to solve it mathematically. Now, we can plot this also, and this plot is simply says we are having almost similar relationship as we are having for the IPR, because this term will dominate. P square means reservoir pressure, that will dominate the situation. The PHF condition will start when this is around 1600. That will be the situation when no flow is happening, and this is Q versus PHF for example. So, around 1600 the value will come out when there is no flow is happening, PHF will come out as a 1600. That can be done simply by saying this Q is 0, no flow is happening, no flow is happening. We can calculate this parameter S, and with the help of that we can calculate what is going to be the PHF value, and this will come out as 1600. Again we can get the AOF, and this AOF says what will be the flow rate at AOF is same what we got in the last example is 1912 or 1913 MSCF per day. Now, the IPR curve will take almost the same curvature, while the equation, this is IP inflow equation, and I can say this is a WPR in our case. What about the outflow equation? From this expression we can say the Q is related to PHF in a direct relationship. We are having y is equal to mx kind of the relationship, where the intercept is where the equation is passing through the origin, and we will get this kind of the expression. So, this is CPR or the outflow equation, and when we are having this, we will get the same flow rate here Q around 1470 or 1478 as we got in the previous example, while PHF can be calculated from the y-axis. What will be the value of PHF? That will come out around 797 or something. Okay. So, now we know with the help of plotting this and this PHF versus Q relationship, we can calculate the PHF and Q. Now, the complexity comes when we are solving these equations, when we are drawing this curve. It is not easy, because at every point we are going to draw this, means we are making this the construction of this inflow and outflow curve. We need to calculate the value of PHF at a particular Q or Q at a particular PHF. Now, we understand this is 0, this is AOF. We can again divide this in 10 equal parts, and we can calculate the PHF from inflow equation, similar PHF from the outflow equation. But in both the cases, if you see this, we already discussed the complexity involved in terms of the F, that depends on Reynolds number depends on the QSC. Similar here, in this case the C is the discharge coefficient, the discharge coefficient depends on the type of the orifice you are using, and on the Reynolds number as well as the diameter ratio of the orifice to the pipe. So, with the help of this kind of the calculation, we can calculate the C value. Now, Reynolds number, again as I already mentioned, Reynolds number is defined like this 20.09 gamma z q y d mu, and to have this Reynolds number we need to have the Q value. So, the iteration is required. Still in the graphical procedure also iteration is required or optimization is required at each node points we are going to have, and we can construct and can get this curve. Then the obvious question comes, if we summarize this, when we are having this mathematical equation, do we need to go with a graphical procedure or mathematical procedure? Because graphical procedure also need the optimization. So, for example, we should go through with both the procedure and check are they equally good or not. In the analytical method, we are just solving one equation. When we club two equations and solving it mathematically, while in other case we are having two equations, those are going to intersect at one point. So, if any conditions are getting changed either in the well bore or in the reservoir or at the choke point, the shift in the curve should appear, and that shift in the curve will tell us the conditions are getting shifted. So, yes, periodically the graphical procedure should also be implemented to have the understanding of how the situation is changing, if at all, in the production system. So, this is the summary of the nodal analysis, and we can see here either we are having the bottom procedure or the wellhead. We are having the bottom as a node or the wellhead as a node. In both the cases, the Q will be the same, while the pressure can be estimated. So, this is PWF and this is PHF can be estimated with the help of this. After understanding this nodal analysis, this type of the analysis can be used to forecast the production, that could be the cumulative production as well as the production rate. Not only that thing, this can be used when the operating conditions are getting shifted, how they are getting shifted, what parameters are going to affect them. For example, if the reservoir pressure is declining over the time, the shift in the operating condition will be observed, and if we are taking the data every month, 2 months, making the construction of this nodal analysis at any particular node, and the shift will say if any changes happens in the reservoir formation, for example, the skin factor and non-Darcy effect or any other parameter that is going to affect, that will help us. Another concept, decline curve analysis. So, this decline curve analysis also tells us at what rate the production is declining, not only the rate of the production declination, but the rate of production rate, how it is going to change, that can be understood with the help of these equations. This is a very standard equation where B and D characterize the nature of this equation, and depend on the B and D value, specifically the D value, because B is just a proportionality constant. The nature of the curve will depend on this D value. It can be the exponential decline model, it could be harmonic decline model or hyperbolic decline model. So, we may discuss all these things in detail later on if time permits. Thank you very much.